Melting ice, chemical or physical? That is physical. Dissolving sugar, chemical or physical?
Can we go back to this one?
Yeah, right.
Can I go? I'll go back to the dissolving sugar, but what do we want to call?
Dissolving sugar.
Dissolving sugar.
Physical, because I think you can back.
It's physical. Burning wood.
Chemical.
Dissolving salt.
Physical.
It's chemical.
It's different than sugar. Why is it chemical?
Mixing red food dye with white cake frosting.
Physical.
It's physical.
Are those candy or ice or crystals?
So the bottom picture I just find neat, but it helps to kind of really draw attention to this chemical or physical issue. So what is happening in that bottom system is we're starting in figure A with a yellow crystal. And as we move through, B, C, D, E is prolonged exposure to light. Okay, so the longer you are exposed to light, the crystal becomes purple. When you remove said light, what happens? It goes back to that yellow clear color.
So would that be physical?
I'll address that just because it's neat. So we heard a suggestion for it being, what'd you say?
Physical.
Physical, which would be fun if that were true,
Well, it's reversible.
but it's chemical. And so this is where I run into issues, is that we hear people say, well, chemical and physical. Physical are reversible. Every process is reversible. Right? If I chop off my arm, is that reversible? With surgery, yes. If I pay someone enough money, they can wire everything back together where my arm is still functional. So yes, everything is reversible, but chopping off an arm, you would not typically reference as being a reversible process. So everything becomes reversible. The amount of energy or effort or money that you would have to expend to cause it to be reversible becomes the issue. And so that's why I don't like the reference to reversible, because there's a threshold that they're referencing on reversible versus irreversible. That threshold isn't obvious. So stop using a thing that has a vague threshold, okay? Which will be extra fun when we continue to push through this in a second. There was a hand?
Never mind.
Okay.
Actually, I have a question. So why is dissolving salt chemical, but dissolving sugar physical?
Okay, so let's go back and look at this one, okay, or those comparisons. And so why do you think both of those examples would have been picked by me to talk about? We did it in lab, and they're like identical processes. We start with a clear liquid, we add a white crystal to it, and we end up with a clear liquid. We get the exact same visible results. Okay, and that's where this becomes challenging, is defining chemical versus physical. Chemical is that you change the bond nature. What's the problem with bonds? You can't see them. Okay? So defining chemical and physical and trying to really nuance that difference becomes very, very challenging if you can't see those connections. So what you would have to do is probe really, really deeply to evaluate what happened at that bond level. In a Chem 130 class, you don't know necessarily what bonds are. So being able to define this becomes a challenging thing to do. Where was chemical and physical first addressed in the textbook? Chapter 3. Where is bonding addressed in the textbook? Chapter 12. The entire process behind chemical and physical has to do with bonds that you haven't addressed. And so we end up using these weird hand-wavy systems to explain chemical and physical. Okay? And admittedly, it's a very challenging concept to get across. There are some that are very clearly chemical or physical. There are some that aren't. Okay? So that's where this whole section, I think, becomes very, very challenging for me to present, because I'm presenting it on a definition that we don't have if we follow the textbook. Because we haven't followed the textbook, we have a little bit more context. But even then, what's happening when we dissolve salt versus sugar? They're both doing the same thing. We're dissolving them. But what's the difference between sugar and salt, which adds a whole nother layer of difficulty to this? So there's an idea. I heard sodium chloride. What is sugar? It was glucose. It's not sodium and chloride. Okay, do better than that, because that's not an element. C6H12O6. So what is the difference between sugar and salt? For those of you being like, I'm going to have to know sugar. No, you don't. Okay? But what is the difference between sugar and salt?
There's more atoms in sugar.
It's more atoms. Keep going. It's bigger. Sugar is all nonmetals, which means the bonds in sugar are covalent. The bonds in the salt are ionic. Those ionic bonds are weaker bonds, such that when we hit them into water and the salt dissolves, we break the ionic bond. A chemical change is breaking a bond. Ta-da! That's why dissolving salt is a chemical process. You literally break the bond. The only way you would know that is if you could drill down to be able to identify what's happening within that. And instead it gets presented as, oh, it's just reversible. Well, define reversible. Okay? Yeah, I could reverse dissolving salt. Can't I reverse dissolving sugar? Okay. Can I reverse burning wood? No? Do you see plants outside? Where did those plants come from?
The soil.
Okay. And CO2 from the air. Where did the CO2 come from? Burning wood. Yes, that is a reversible process. Is it easily reversible? No. Does it take time? No. But it's reversible. Okay? So deciding where that threshold is becomes very, very challenging. Okay? Because we're saying it's black and white as chemical and physical, but then that reversibility is on a threshold. And that reversibility becomes a challenging one to look at. Instead, what we should be evaluating is that chemical and physical are not black and white. They are on a spectrum. And deciding what's happening between those individual processes really means you have to understand what is happening at those levels. To understand what's happening at those levels, you have to drill really, really, really deeply. Right? Having that ability becomes a very challenging thing to do, and that ultimately is going to rely on your experience with that. Right? So one of the fun examples that we could address is we could talk about dissolving of tang. How many people know what tang is? Okay? So not everybody raised their hand, and a couple people were like, I think I know. Okay? You go back to a certain age range of people, and they're all, yeah, I know what tang is. Okay? Because we grew up with it. Okay? So everybody's outside experience changes how we can ask a question. Okay? And that's where that chemical and physical becomes challenging. So how can I ensure that I can now ask a question about chemical and physical? I could ask you to define them in a short answer. I could ask a multiple choice based off of these examples. Why can I use these examples? Because we've now talked about them. So I can address that. Okay? And so those personal experience types questions are neat because it's trying to bring in the outside world, but not everybody has those experiences, which means those questions students could be getting them wrong for the wrong reason. Not for a conceptual misunderstanding because they just literally don't know what that is. Okay? So with chemical and physical, what I really want you to get out of it is that it's a spectrum. That's why that line rainbow is up there. At one end of that spectrum, we've got physical. At the other end, we have chemical. And there are all sorts of different processes that fall within that spectrum. Some are very cleanly physical. Some are very cleanly chemical, based off of reversibility, okay? Or the ease of reversibility. Some of them, like dissolving salt, because it's nice and easily reversible, okay, which would suggest physical, but if you get down to the chemistry of it, you're literally breaking a bond, makes it chemical. So you'll notice for each of these, I color-coded them based off of the rainbow spectrum. That dissolving salt is effectively dead in the center between chemical and physical. So much so that if you go online and look up, is dissolving salt chemical or physical? Everybody likes to fight on the internet. It's literally divided into a 50-50 camp. Half the people arguing say it's physical because it's reversible. Half the people say it's chemical because you're breaking a bond. Okay, so depending at which camp and which definition you're working with, you change your interpretation. Both of those camps are ultimately wrong because those camps are making the initial assumption that's invalid. It's not chemical or physical. You can blend those. Okay? So it's an entire spectrum of it. Go for it. Right? So let's go to this last one, because John had an interesting point. I think it was you, John, that said that that was physical. No? Somebody else said it was physical. You said it was physical. Okay? Said it was physical, because again, it was an easily, or you just turn off the light, it reverses. That sounds pretty easy. Okay? If you drill down into it and look at what's actually happening on an atomic scale, that ultraviolet or that light that you're shining on it causes the bonds to change in the molecule. Because the bonds change, the color of the sample changes. You've broken bonds. That's by definition chemical. It is an easily reversible process. Right? So it would suggest physical, but it is literally a breaking of bonds. Okay? And so that's why we have to be careful when looking at chemical versus physical to not overemphasize on what you can see, because there's usually a whole lot more there than what you can see.
So because it is easier for us to get it wrong, you're going to ask it on the test?
No. In fact, this is one of the questions I've increasingly been pulling from tests, because it's a difficult question to ask. One place where I would potentially put it would be in provide a definition for chemical, a chemical change. Provide a definition for a physical change. Okay? And potentially with that, be like, provide an example. Okay? Because you should be able to pull from your own experience an example, okay, based off of your understanding of those definitions. Your experience may be different than mine, but as a grader, I have a different benefit than you. I have the internet. I can look up your experience and be like, what the hell is that experience about? Oh, okay, that's what it is. Yes, that's chemical. Or yes, that's physical. Okay, does that make sense? Yeah. That does make it a more challenging question for me to grade, but it still gives you an equal opportunity to present that knowledge. Make sense?
What's the
Okay.
stone?
Say that again?
What stone is that? You said you were going to tell us.
What?
I'm sorry, crystal.
Oh, it's what's known as a photochromic molecule. That was one I actually tried to get my organic class to make, but I couldn't get it to work. And if I don't get it to work, I don't make students do it. But it's known as photochromic. If you've seen not sunglasses, some people will buy really fancy seeing glasses, reading glasses, that when they go outside, the color changes. Okay, so that they can still see, but they don't have the sun blinding them, and they don't need to wear 2 pairs of sunglasses or 2 pairs of glasses. The material to put into those glasses is that. I don't know that you can necessarily buy it easily. I know you can make them. They're called photochromic or photochromic molecules. So the research lab that I joined at ASU when I started grad school there, about half the group was working on molecules that would do that. So it is kind of neat stuff, and you can go through and make it. If you're interested in that, you can talk to me and I'll give you more on it. But beside the point, let's keep going. So this gets us to states of matter or equations. So we've got an equation here. What does it tell us? Okay. We have phases specified in the parentheses. So we know the phases of the materials that went in here. The AQ is an interesting one, and you use the proper wording there. That's not a standard phase of matter. Okay. Our standard phases of matter that we're concerned about, solid, liquid, gas, what the heck is AQ? As you suggested, it's a solution. Okay. What is a solution? I take a solute and a solvent. I take some substance and I dissolve it in a liquid substance. That is now a solution. Okay? AQ doesn't look like any aspect. In fact, none of the letters in AQ show up in solution, because solution is a very broad category. AQ is actually a very narrow category within solution. What is it in reference to? Acids isn't a bad place to go, but that assumes you also have the H in front. We haven't defined whether it has an H in front or not, so it's not acids.
Liquid?
It's in reference to aqueous. If you were thirsty and went to the water machine.
Water fountain, you were close.
I know I didn't want water fountain at all. The box you put money in and stuff comes out. Vending machine, there we go. The vending machine, and you were thirsty, you could put some money in and you could get out a bottle of water. That water sometimes is branded
Aquafina.
Aquafina. Why do they call it Aquafina? Water fine. It's literally saying that you have clean water. Ta-da! That's the brand of Aquafina. Aqua is your root for water. AQ is in reference to that water. So an AQ is meaning that we have a solution, but in particular that solution is using the solvent or the liquid form of water. So it's whatever we put into water. Okay? So that actually adds more information in this expression because we now also know water is present.
So when
Okay?
writing-
Even though it's not explicitly stated in our equation.
When writing the other version of it, would you write DH2O?
You would not include H2O. H2O is not part of the chemical reaction. And so that becomes the next part, is what we're seeing here is a chemical reaction. How do we know it's a chemical reaction? Because of the arrow. Okay? In that arrow, because it's a chemical reaction, as John was suggesting, this means bonds change. Why do I not include water in it? Because water's bonds aren't being made or broken in this process. It's just present.
So we just assume the AQ is water.
It's not an assumption, it's an explicit statement. AQ means water is present.
No,
Period.
I mean like we put it in our.
You would have to write AQ as a parentheses. You would never write H2O in your equation unless it was actually a case of bonds forming, okay, or breaking. So what else do we have in this? We have states of matter.
The two elements being changed into two,
Okay, how do you know you have two?
because A and B.
Is that two?
No.
No. So how do you know it's two?
Addition
A
sign.
plus B.
Okay. We have these mathematical operators. When we're looking at our chemical equations, they're always going to be an addition. You are always adding something in there. Okay? But it's actually slightly different meanings. Okay? The plus on the left-hand side is an adding. What is the plus on the right-hand side?
Multiply.
Separation.
It's not multiplying.
It's like they are
Combination of them.
working together.
It's really just meaning an and. Okay? So that the plus on the left-hand side means those two things are coming together. When I move to the right-hand side, I'm saying these multiple things are produced. Okay, so the right-hand side is really an and. The left-hand side is actually a descriptor of these things are coming together to do something. Okay, which brings in, say that again?
That's not confusing at all.
That's very true. Okay, but there's another piece to that you haven't also explicitly stated, which helps to explain why we have slightly different meanings with that plus sign.
Reactant to product.
These are reactants. These are what are coming together to make something. And then these are products. These are the end result of having done so. Right? That's what's changing the meaning of our plus signs. It's a very subtle change to the meaning, so don't kind of overemphasize that, but it's recognizing the difference between reactants and products, okay, and acknowledging that they have different roles in our overall reaction. Does that make sense? Go for it.
I just want to point out that he is laying out one of the most, or to me, what seems like one of the most important writing systems in chemistry. He's helping you know how each of the pieces fit together, naming and labeling each of the morphemes and establishing the relationship between all of these pieces. This is core and key. If you did not put this on your notes, you're losing out on this on the key structure for chemistry for this writing system. Again, he's labeled the morphemes for you, the individual pieces of language. He's talked about how they fit together and what they mean. If you don't get this, it's going to become detrimental long term.
And so that becomes also one of the extra kind of bizarre things that kind of goes with this, is most of this kind of just becomes implied. We just kind of assume you pick this up. We're actually clearly explicitly stating it because it's important. You have to be able to know that to draw information out of this. Okay? There's actually more information stored in here, but first we'll get your question.
So the gas, liquid, solid, and the aqueous, are those gonna be like permanent spots for them, or are they interchangeable throughout the equation?
I think I see what you're saying. So that if I wrote another equation, the gas has to be first in the list, followed by the... No, that doesn't matter. The symbol for the phases, and this is actually why I don't teach 151 and 152, you're supposed to always include the phase. The phase is always specified in the lower right-hand corner after you've given your entire compound information. Okay? Sometimes you'll see it slightly larger because it can be more difficult to read as a lower right-hand corner. Okay, so sometimes you'll see it popped up like that. Okay, but it's shown after that sequence. Where they fall in the equation, completely arbitrary. That just depends on what you decide. Okay. To that end, I could say A gas plus B liquid. I could just as easily say B liquid plus A gas. The order in which they appear on any side of the equation doesn't matter.
But it couldn't be A gas plus B solid.
If B was a solid, then yes, you could specify B. So the phase has to get specified, and when we run a reaction, we would just need to include those phases. So what I think you're getting at is that if we wrote a new equation, say like this, which we've looked at already, okay, right now I would say that's a wrong equation because we haven't addressed the number, so we don't worry about that yet.
It's not balanced.
That's the number.
There's no phase.
Okay, so we could reference based off of our general format. This was two things to make one. Up here, this was two things to make two things. Okay, well, if this is the format of an equation, then this must be wrong because I didn't form a second thing. You don't have to form a second thing. You don't have to start with two things. You could start with one thing. You could start with three things. Okay, so the exact number of each of those pieces could change. But the format is always going to start out, yes, you can start with just one thing. You're like, no way, there's no way that you could start with one thing and end with multiple.
Isn't that where like the starter reaction?
How many things do I have? How many things do I have?
Physical change.
Okay, and for the record, that is not real. Well, it's sort of a physical change because it's still a piece of paper, but I've now broken those. That would be where the types of equations, types of reactions come from to overlay with that. Okay, so this is still just a general format. Okay, so I like that you pointed out that we didn't end with two things. This is still a valid equation. Okay, I'm still allowed to start with two and end with one. So that's not the problem with this equation. We don't have the physical states. You should specify the physical states. To Tasha's point, she was saying, well, shouldn't that be gas, liquid, and now we'd run into a problem. What is H2O?
I guess.
Solid or aqueous, according to the format. So we might say, well, it's aqueous because it's the last thing there. Okay? Does it really make sense to say water is in water?
Yes.
Okay? That's not a very clear thing to state. So we wouldn't say that's a solution. We would call that for what it was. That was a liquid. And now we're breaking from your pattern of saying, well, but isn't that where they're supposed to show it? No. The phase has to show up next to those. Yes, that is absolutely true. But does it have to go gas, liquid, solid, aqueous? No. And in fact, when we look at that bottom equation, H2, yes, is a gas. O2 is also a gas. Okay? It is not a liquid. Okay? And I hate it when that happens. Okay? To make it a liquid, we would have to get exceptionally cold, and our concentration would now go through the roof, that if I mixed hydrogen gas with liquid oxygen to try and do this, it would probably explode me in the process. Okay? Because of the sheer volume of those substances. Okay? So in this case, what we're seeing is, again, the phases need to be specified. What that phase is, sometimes you're responsible for, sometimes you're not. How would you know O2 should be written as a gas?
Because it's on the periodic table.
What do you mean it's on the periodic table? Yes.
It's in the top right corner.
We look at oxygen. How do we know that's a gas? It's red, it's a gas. Okay? So those phases are things that you can predict for certain things. H2O, how do you know that's a liquid and not a gas? Say it again. Common knowledge. So there's some things that are common knowledge. Okay? Most of the reactions we'll study and look at aren't common knowledge. So how would you know what the phase was? You are told. Okay? You just have to make sure you specify it in that equation. Okay? So what we've now done is kind of broken that apart to look at all those pieces. The textbook goes through and addresses a lot of this, but I actually want to draw in one more piece of information that hasn't been pointed out yet.
Can more be added to it? So say you got another plus sign. Can you do that?
Could I add another plus over here and say, what do we have letters? E solid? Yes.
You can.
That is
And
fair
it would
game.
just be the same. Like it would be
And
the
so
same
one of the things,
meaning,
same, say it again?
like the same meaning as like the adding and then the and.
Yes.
Yeah.
Okay. There's another layer that we could put into this. Does it have to be E solid? Maybe I need another A gas to run this reaction. That would be a bit silly to write it out that way, right? I do see you. Give me a sec. How could we rewrite that? We could put a 2A. So one of the things that you guys didn't specify yet was that this chemical equation actually gives you another piece of information. How many of each of those things were put into the chemical equation and how many came out? Right? There is an implied number in front of each of those. That implied number gives us an amount for that substance. Okay? When we started the initial equation, what was that implied number?
2 on the left, 2 on the right.
1 in front of each, so 2 total on each side. Okay? You're responsible for knowing that number and ensuring that number is correct. To ensure that number is correct, as some of you were pointing out, you would have to balance the equation. This is not one we can balance because we don't know what A is. We don't know what B, C, or D are. They're too generic to be able to do a balancing expression. Okay? Yeah.
So in every single equation, the phase has to be specified.
I really hate saying yes to that, but yes.
Wait.
Right. And the reason I hate saying yes to that is I don't like specifying phases.
Well,
I've never seen it up
so we
until
don't,
now.
so we don't
Yeah.
have to do it like on the play bus if you didn't have it was
I dislike specifying the phases so much that my reflex is to not specify phases. You should be specifying phases, and you can give me a hard time for not specifying phases every time it shows up.
Can we just not do it on the test?
No, you've got to make sure you do it.
Dang.
If you have the information, you need to include it. If you don't have the information, that's a whole nother can. You don't have it. You can't put it in because you don't know what it is. But if you are told that it is a solid, you better write parentheses S at the end of it because you have that information. Okay?
So if you just put the formula, just the formula, we don't have to write. Yeah, if you write that, we don't have to write it.
Okay? Just like we just walked through, could you put phase information into this?
Yes.
Yes. What phase information could you put into this?
Yes, yes.
We know these are gases. Why do we know those are gases? You know that from the periodic table. Could you put in water was a liquid? Why do you know that? That's common knowledge. Okay? If I switch it up to know all of these. This, maybe you know all of these. Could you specify phases?
Solid gas.
Solid, gas,
And solid.
I don't know what I said. Oxygen.
I think it's
It's rust.
it's rust. Is that common knowledge? For you, that was. For you, that wasn't. Okay? So, in that statement, you wouldn't know what that phase was.
It's in the playbook.
Me ask, damn it. I was trying to give you one that you didn't know. Okay? If you didn't have that as common knowledge, you wouldn't be able to specify it. For these two, you are expected to know those because those are straight off the periodic table. Does that make sense? So a lot of it comes from that context. You have to be aware of that context. Okay? So the textbook has this nice slide that gives all of that information and summarizes it. It's all pretty much there. The one thing, or the two things that I'll throw in here is different. Sometimes you'll see a delta written either above or below the arrow. It does not matter whether it's above or below. Usually it's actually below, not above. Okay? That delta means change, and in particular it means change in temperature, okay? And a positive change in temperature. So if you see a delta, that means you're adding heat to the reaction. Right? You may see a single metal or sometimes more complex things written over the arrow. In this class, that means that is a catalyst. Okay? It's what helps the reaction occur. That ends up being a catalyst. Okay? So, before we dig into our equations too much more, conservation of mass. You can't create or destroy matter. So mathematically, what does that mean for us? Let's take a look at two examples at the bottom. 1 gram, let's try that again. We'll do 2 grams and 3 grams. How much water would I make? 5 grams. How'd you do that?
I added to.
You're like, I just added 2 and 3. Yeah, that was a dumb question, Mike. Okay.
Okay.
I hear you. 2 grams plus 6 grams. How much water did I make?
None.
How much water did you make?
How much water did I make?
Estimated guess 4 grams.
Why now all of a sudden the pause? You're like, you just add the numbers together, Mike.
4 and 4. Let's go.
Yeah, it's just
Okay? It could have been 4 and 4. It could have been 2 and 6. It could have been 6 and 2. It could have been 1 and 7. It could have been 7 and 1. There's an infinite number of possibilities that come out of that. Okay, we didn't even talk about the decimal values that could have been attributed with that. So when we're looking at our conservation of mass, we can use that in certain situations to predict the mass of a product. Okay? So what was different about the examples given? Okay, we provided a number here, and you had to predict one thing left over. You're given a number here and a number here, and you were asked to predict. I actually asked you only to predict one thing. Right? But to predict that one thing, what do you also need to know? You would have to know that one. Okay? So to go through and solve this, you have to have all but one piece. Does that make sense? So be careful with that with conservation of mass. Okay? During a chemical change, this is where we get Proust comes in with the law of definite composition. This was added to and built on and absorbed by Dalton. Okay? And really what this said was that when we run a reaction, when I make water, okay, take H2 plus O2, and I make water, what I found was regardless of what I started with over here, if I started with 2 grams of water, it required 16 grams of oxygen. Okay? If I started with 4 grams of water, it required 32 grams of oxygen. Okay? If I started with, I'm going to need some help, 6 grams of hydrogen, I needed 48 grams of oxygen. Okay, so 2 people started to pick up on a pattern. What was that pattern?
It's the atomic number.
This was 1 and this was
8.
8. And so they were multiples of each other. 6? Oh, no, that's right. Okay, so that's the law of definite composition. That compounds always contain the same elements in a constant proportion by mass. Well, when I look at this, does that show mass? No, the chemical formula doesn't show anything about mass. It says the number of atoms. Why was Proust looking at mass and not the number of atoms?
Because at that time you didn't know the atoms.
He couldn't count the number of atoms. So the only thing he had was mass. Okay? And so that's why he was able to pick out that mass proportion. Okay? Why was it 1 to 8 in the case of water?
Hydrogen has one mass and oxygen has 8.
Try again. You've got the right idea, but break it down a little slower.
What's the question?
Hydrogen has 1 mass.
Uh-huh.
Yes, I agree. Oxygen is not 8, though. Oxygen is what?
16.
16. Why 1 to 8?
So it's a number.
There are 2 oxygens. So when I build out water, each hydrogen weighs 1, but there's 2 of them.
For water, yeah.
So it's not 1 to 16, it's 2 to 16. A fully reduced ratio would be 1 to 8. Okay? But that's why we started with 2 to 16, because that was the easiest math for me to do in my head. Okay? And I didn't show 1 to 8, because 1 to 8 would be confusing, because it's mass of oxygen is an 8. Does that make sense? Okay? That's what Proust was discovering, was that when we did these reactions, and we were able to react at all, that we had these constant proportions, that there was always a constant proportion of 1 to 8, hydrogen to oxygen by mass. That would not be fun to write into our chemical equation. Right? And for those people to be like, well, why not? Okay? When you make bread, how do you make bread? Not bread. Try again. A sandwich. Make a sandwich for me. What do you got to do? How? Say it again. 2 slices of bread, and that's all we need. We can stop right there. You didn't say, I need 500 grams of bread. Okay? You said 2 slices of bread. When we build chemical reactions, we're looking at the number of them because it's easier to represent the number of those pieces as opposed to their mass. That mass requires a measurement. The number doesn't require a measurement. That's an easy counting process. Okay? The thing that I found interesting behind this is how the hell were they able to figure all this kind of mass stuff out? Okay? There are a couple different examples that we could look at, which aren't a big deal, so don't stress about them. The easiest one we can look at would be potassium chlorate. Potassium chlorate, that when I heat it up, turns into potassium chloride and oxygen. I can see that constant mass proportion because I can change the amount of potassium chlorate I use, okay? And I can see that the end of that heating process, I end with the same mass proportion, potassium chloride, to what I started with. And that allows me to see that mass relationship. Okay? So there are ways to go through and do this. These are all ultimately old school methods that have not entirely disappeared, but mostly disappeared because we've got better techniques. Those better techniques you'd see in different semesters.
Okay, so on the equation that you used it for, was that equation wrong though? On the, like
H2O?
H2 plus O2.
We haven't addressed that yet. Don't worry about it yet because we aren't there yet.
Oh, okay.
We should see that.
Okay.
Okay. Dalton comes through, adds Proust's theory into his definite composition. Okay. Compounds contain atoms in small whole number ratios. That's effectively an adaptation of Proust's law of definite composition of mass. Right? Just for the record, 5 rules of Dalton, 2 are false, right? Which 2? 1 and 2. What disproved 1? The existence of neutrons, electrons, and protons. Was that all done in one experiment?
No.
No?
It was across 3 or 4 different people.
Yep. So where was it first disproved?
Rutherford.
Rutherford's usually is an okay guess, but it's not the first. Rutherford proves we have a nucleus with the gold foil experiment. Okay?
Plum pudding.
We weren't even getting to looking at the existence of a nucleus until we had plum pudding. Why did we have plum pudding? We had Thomson with the discovery of electrons. Right? That was using our cathode ray tube. Number 2, all atoms are identical. What makes them not identical?
Ion.
They don't all have the same mass, so we're in reference to isotopes based on differing numbers of neutrons. Ions are also important. Sodium metal versus sodium ion. Sodium ion, you live. Sodium metal, you die. Okay? That's a pretty big difference. Okay? It's still a sodium atom, but the chemistry associated with it is drastically different. What's that difference between a sodium metal and sodium ion? A single electron. You remove one electron, you go from death to life. Right? That's a pretty big difference. And that's not death to, I just didn't die. That's death to life. If you don't have sodium ion, you're dead. Okay, so you need sodium ion to live.
It's aluminum, not the red one. Just out of
Probably,
curiosity.
most of these discoveries were probably made by someone epically failing. Yeah.
That's why I call it periodic table the Horcrux of science.
So do you know what the difference between like iodized salt and then just kosher salt would be?
Iodized salt has iodine added to it. It's not ionized salt. Ionized salt is salt. Okay, so if you're seeing something called ionized salt, it's a marketing scheme to make you buy it because you're like, oh, that sounds fancy. Yeah, don't give science to marketers. Chemical reaction. So here's a chemical reaction. This would be a word equation for the record. Okay, so we need to convert this into a chemical equation, so our chemical language. So how do we go through and do this? What do you see?
Sodium.
Okay, so I see sodium, which means it means Na. It doesn't necessarily mean salt, because that's going to depend on the next atom. Salt also has a nasty connotation with it, a deep connotation that you associate it with sodium chloride. Salt actually means nonmetal and a metal. Okay, so what's the next atom?
Hydrogen.
Hydride. What's our symbol? H. This is a tricky one. I do apologize for that. You rarely see hydride. Okay? But it's kind of a requirement for one of the secondary pieces of information I want to get to. What else do we have here? We now have a substance. I see your question. I'm going to potentially hold you on that. This says reacts with, which means? Reacts with. It's a plus. Okay? Before we get too excited, what did we say, Ernesto, about phases? Do you need to include the phase for sodium hydride? Does anybody have the common knowledge of what sodium hydride is?
It's a solid.
No, but it's specified in the statement. Should you be writing solid next to it? Yes, because you know that.
But you didn't.
Okay? You know that because it is given to you.
But he didn't.
We left space for it.
Oh, okay.
That was intentionally why I left that space. Okay, so wait a sec, because John, you had a question?
So why would hydride just be an H, the letter H for hydrogen? It's a different name.
So hydrogen, you're right, we should see that, whatever those other letters are, O, G, Y, N, I'm missing some letters, but yes, we should be seeing that. So why is it just H if it's hydride? Okay, remember when we're looking at our nomenclature, the IDE is a suffix changer when looking at an ionic compound. Okay, so that means that was our anion, our negatively charged species, was the ide. If we were going to revert back to what was the element that made that, we now need to look at the root of that name and hydro, or hydr. What element has hydr in it? Hydrogen, that's how we know it's an H. Okay, and not anything else. If it was going to be a ternary compound where it needed multiple elements, there's an interesting thing that's going to change in that suffix. That D won't be a D. It would be a T. Okay? Which would be a dead giveaway that we're looking at a complex ion that we need another element. Because it's a D, it's a pretty big tip-off that we're looking at just a binary ionic compound, and it's just the element by itself. Okay? There are two exceptions to that, hydroxide and cyanide. And when I said that, hydrox ide. Do we have hydroxide? No. Okay, so that's why it goes in just as H. We good? Ish? Yes. Okay, what's the next thing we got?
Acetic acid.
Okay, we have acetic acid. So within that, what do we see? Okay, and I already heard someone say acetate, which is technically correct, but that's like the most advanced form of that, so cool. Okay, we see acid. What does acid mean? H and aqueous. Okay. We could then break down our roots again. The acid part, okay, comes from the root that made it. This is a ternary acid because it doesn't say hydroacetic acid. So we know it's ternary. Okay, that means we need multiple atoms. To know what that multiple atom is, we would look at that root, acid. Okay, the ick means that its parent came from ate. I ate too much, so I got ick. Okay, so it's got to be acetate. The formula for acetate, C2H3O2. How do you know that? You were actually told to memorize it, so you should be working on that. To produce means reaction arrow. We move to the next one, our sodium acetate. We've got our NaC2H3O2, which we happen to know is aqueous because it says so. We've got our plus for our and then we've got our hydrogen gas, so H and G. Okay? For those of you panicking, hold on to that thought. We'll come back to that in a second. Okay? Before we decide to do anything else, we need to make sure that each of our formulas were actually correct. Okay? All we did was pull information down, the names of those pieces. We didn't actually ensure that what we produced were proper formulas. How do we know we have a proper formula? We balance what? No.
Left and right of the arrow.
Nope.
Mass.
Not mass.
Matter.
Proper formula. Where do you see a proper formula? What about NH makes it a proper formula? Looking across the equation is irrelevant. That means you have a proper equation. We aren't there yet. You have to make sure that formula is valid. How do you ensure that formula is correct?
By knowing the numbers associated with it.
Knowing the numbers.
The charge.
Charge, there we go. We would have to know the charge on each of the pieces of our formula. Sodium, you are required to know is? Plus one.
Let's go.
Hydride's a trickier one. This is why I apologize for that. Is a -1. Is that formula correct?
Yes.
Yes.
We know it's correct because
It's
the charges balance out. We move to the next one. The hydrogen, in this case, not hydride. This is why I'm apologizing on the hydride. The hydrogen is a +1. The acetate is -1. How did you know it was a -1? That's an awful lot of stuff there.
You had to remember.
You are required to memorize the charge on acetate. There are 6 polyatomic ions that you have to know. Name, formula, charge. So that formula is correct. The other side of the equation, we've got sodium, which was a +1. We have our acetate, which is a -1. So that formula is correct. Now we move to the H. Well, there's nothing really to balance it out, so it must be right. No, it's actually H2. How do I know it's H2?
Because you got 4 hydrogens on one side.
Nope.
No,
It's a diatomic molecule. There are certain elements that when they are by themselves, okay, and not ionized, that they are written partnered with another atom. Hydrogen is one of those cases. It is a diatomic molecule. We have to write it as H2. If I wanted to write it as H, what do I have to change? Okay, so this hydrogen gas is equal to H2. Okay, if I only want to talk about hydrogen atom, what language do I use?
Lewis dot structure?
I want to talk about it. If I want to talk about hydrogen atom where I'm just referencing the H, what language do I need to use? What was that language I was using? Yes.
Linguistic?
No, I know where you're going. Stop doing that.
Great, you're affecting us.
Well, linguistic means language. He said, what language do I use? So saying linguistic is just repeating that. It's not being specific.
If I want you to say H, if I want you to write the symbol H, what do I need to tell you?
Write this in.
Hydrogen atom.
Oh, okay.
Okay? So if I say you're working with hydrogen gas, the symbol is?
H2.
If you're working with hydrogen, the symbol is?
H2.
If I want you to work with hydrogen atom, the symbol is?
H.
H. So the only way you write just the single element is when you are told just that single atom.
Is that
You have to see that word atom associated with it. Is it with just H? No.
okay?
Okay? We'll look at that in a second. I believe that's actually hidden underneath all of this, which we'll see here in a second. Okay? Kind of, sort of? So that does suck because we have to memorize that. And yes, we'll show that what you have to memorize here in a second. Okay? But you guys have been chomping at the bit to do the next part of this, which is
Is that
balance the whole equation. Make sure that we have conservation of mass. So we could go through and look at the mass of every single atom. That's a lot of math. There's an easier way to do it. Okay? If I have a pen on one side of the equation, what needs to show up on the other side? A pen. Okay? So if I have one sodium on the left-hand side, what needs to show up on the right-hand side? A sodium atom. It can change its location. Right? So if I start with 2 pens, and I'm going to do a reaction now. On the other side of the equation, I still have 2 total pens. The mass is still the same, but I've changed the connectivity. Yeah? Okay? That's what we're talking about when we're looking at balancing an equation. So the process for this is really just coming up with a notation that we can consistently get things right. My reference is to start with your elements, put it underneath your reaction arrow, and just count them out on both sides. So the left-hand side we have how many sodiums?
1.
Right-hand side? 1. How many hydrogens on the left?
4.
4. 5.
1 plus 1 plus 3,
5.
5. How many on the right?
5.
3, sorry for the sloppy 3, and 2 gets us 5.
You can't just write your acetate,
I'm not going to do that right now,
but you could.
but you could. How many carbons on the left?
2.
On the right? 2. How many oxygens on the left? 2 and 2, which means the equation is balanced. I don't have to change any numbers. So this is a really straightforward one. I don't have to do anything fancy with it. Okay? I can still ask a multiple choice question about this. I could ask, what is the coefficient in front of acetic acid?
1?
Okay? To answer that question, you have to know that acetic acid has the formula HC2H3O2 so that you can write out your equation. And then you also have to know that the coefficient in front is the number in front of that, which in this case wasn't specified, but is an implied 1. So your answer is 1. I could ask for the sum of the coefficients on the reactant side of the equation. It's 2. The coefficients are the numbers in front of each of these things. I said only on the reactant side of the equation, which means 2. Okay? I could do that just as easily for the product, and I could also say, what is the sum of the coefficients for the entire equation? 4. Okay, so those coefficients are referring to the number out in front for each of those. Kind of, sort of?
What do you recommend in hydrogen and oxygen class?
So there are different recommendations on how you go through, on what elements you go through to pick to balance. Okay, so we heard 2 suggestions come out of this. Kira suggested, well, couldn't you have just balanced it as C2H3O2 instead of breaking it into each of the individual elements? Yes. Okay, that does simplify it and complicate it at the same time. Okay, why? How many hydrogens would be on the left-hand side of the equation?
Still have 5.
You would have 2. What? That makes no sense. If we balance this as C2H3O2, how many hydrogens are on the left-hand side of the equation? There's only 2 because that piece, all of those hydrogens are embedded in that C2H3O2. So if you go through and balance it as these bigger pieces, okay, you have to be careful that you don't start double counting atoms. Okay? The other thing, when can you do this?
Only with an acetate.
Not only with an acetate, because there's actually cases where you can't do it with acetate.
When it's on both sides.
When it shows up the same on both sides of the equation. If I see acetate on the left and I see acetate on the right, now I can do this. Okay? Because that is now a unit that I can group and balance it out as a group. Okay? Some people really, really struggle with that. Okay? And need to balance it out by atoms. That is entirely on you to decide what your preference is. Okay? Damn it. What did you say?
Oh, don't you recommend hydrogen and oxygen last?
Oh, yes. In our balancing process, generally it is a good idea to balance hydrogen and oxygen last. It is not a requirement. Okay? The reason being is that hydrogen and oxygen tend to show up in a lot of different places. So if you have hydrogen showing up in 3 different places in the reactant and 3 different places in the product, and they don't balance out, which one of those 3 places do you change?
That's by itself.
Okay? Now it becomes confusing. That's like our law of conservation of mass, where we had 4 things. Because we could change one, which could work to balance it, but it could also entirely shaft your entire balancing process. So that is why you tend to leave hydrogen and oxygen for last and hope that by balancing all the other things, you don't have to worry about it. And they self-balance. Right? And that's why you would leave them for the end. Okay? So again, not a requirement, but it does simplify things. Okay, so there's our equation. The diatomics, there are 7 that you are responsible for. All the way back to high school, have no fear of ice cold beer, and you've now got them. Ta-da! H for hydrogen, N for nitrogen, F for fluorine, O for oxygen, I for iodine, C for chlorine, which isn't perfect, but it's close, B for bromine, which again isn't perfect, but it's close. Okay? Okay, so if you remember that phrase, you now have your diatomics memorized. Okay? There is another approach, so we'll give you 2 more approaches. Let's identify those up on the slide or up on the periodic table. We've got nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Right? What does that shape look like?
A boomerang.
How many of these did you have to memorize? There's 7. Look at that. That's perfect, right? Except how many did I circle? 6. Oh, that's right, because I forgot one. So that kind of tips you off. Okay. The last one works by having these circled. Doesn't work out so great with the state of Arizona, but if we were Canadians, it might make a lot more sense. This looks kind of like
I don't know. Not really Canadian.
a hockey stick and a puck.
Oh, okay.
Okay.
No, doesn't say, but okay.
I don't necessarily agree with it either, but that's what I was told. And actually by a hockey player. They were like, it's a hockey stick and a puck. I was like, whatever. Okay. However you memorize that is up to you. Okay? But you need to know that when I ask for the formula for nitrogen, the symbol I'm expecting you to write is N2. When I ask for the formula for chlorine atom, you would write Cl. Why not diatomic now?
Yes, the atom.
Because I asked specifically for that atom. You have to see that atom word there. If you don't see it, you should immediately be specifying diatomic. Okay? Kind of, sort of? Cool. So, balancing chemical equations, they have to balance out on both sides. We actually already walked through that. Okay? So, guidelines for balancing. I break it down into 7 steps. So far, what we looked at was actually steps 3 through 5, 3, 4 actually, with the one that we did. Okay, we didn't have to predict products. Okay, sort of did. We were given names, so we had to make sure that those structures were correct. Okay? Sometimes you'll have to look at a reaction and be like, I know that's a double replacement. That means these products are formed. Don't know what those terms are yet? That's because we haven't talked about them yet. We'll see that.
You talked about it in your
I did talk about it in the video. Okay? So we're trying to move through those 7 steps. Okay? The hardest one for students to really kind of deal with is that this is a sequence that you constantly cycle all the way through. Okay? We started with sodium, we moved to the next atom, we moved to the next atom, we moved to the next atom, we moved to the next atom. We didn't go sodium, next atom, oh, that changed some numbers, back to sodium. Cycle through all the way through, then loop back, go all the way through again. We'll look at examples here in a second to see how that works.
If you see that it's not going to balance.
You will see that it will have messed up. That is absolutely true. You're like, but shouldn't I go back and fix it?
Yeah,
No, because if you continue through, guess what may very well happen? It self-balances. Okay? And if you go through prematurely to start changing numbers, you're constantly changing things. You haven't actually finished a cycle. Okay? So get something down so that you can then look at it and decide, do you need to cycle back? Okay? You could look at this as draft work almost. Okay? When you're building that draft, you constantly go through. You're still putting words down on a page. Okay? If you decide you write your first sentence, I don't really like that first sentence, and you constantly spend time looking at that first sentence, you may have a great first sentence, and you have nothing else. Okay? Get that information down first so that you can go back and then start refining that process. Okay? And it's suggestions. You don't have to do it that way, but it's suggestions to get it consistently right. The next one that gets kind of irritating is the check your work. Repeat your steps 3 through 5. My recommendation is you should go back and check your work until you are irritated that I am making you check your work. Just build a little bit of an emotional tie to it that you want to punch me. You will remember your steps better. Okay? Don't actually punch me, for the record. Just a little bit. Okay?
So you're
Then
saying
you can go through.
want to.
You can want to as much as you want, just don't do it. Okay? Then you can go back and check that your numbers are all the smallest possible numbers, because it is possible that you somehow skipped a process and you've now put in too high a numbers across all of them. Okay? So there were 4 examples that were on the slides, I think, in Play Posit. Okay? We're going to look at the first one here. And then I'm going to give you a different example. Okay? You want me to do the second one? I can do that.
No, I was doing it already. Yeah, I was just copying it. That's it. Don't worry.
Okay. Second, it doesn't affect me. Okay? So, the first thing that I've noticed, I'm getting a lot of people, interestingly enough, I don't know if it's military necessarily that is somehow instilling this, but people from the military are coming back and complaining about this and say, well, why can't you just say plus H plus BR? Right? Isn't that balanced?
Technically, yeah.
Yeah. You just didn't use all of the pieces. Okay? And where I would argue this kind of comes from, let's say I'm going to make a cake. Okay? When you make a cake, do you use all of your ingredients? Right? You're going to make chocolate chip cookies, you buy a bag of chocolate chip cookies, right? You don't use the entire bag in your cookies unless you're making a crap ton of cookies. Okay? You've got some left over. This format matches that kind of leftover thing. Okay? In cooking, it's okay. In chemistry, it's not. Why is it not okay in chemistry? Okay? In cooking, those leftover chocolate chips, what are they going to do? They're just going to sit there. It's not going to be a big deal. This hydrogen left over, guess what it's going to do? It's going to start a fire. It's going to react. Those leftover pieces are so reactive that they can't exist on their own, that they have to continue to react, which means that equation doesn't make sense because I will never get a hydrogen atom on its own. I will never get the bromine atom on its own. Okay? So the equation you're looking at gets you to the most stable state. okay? The state that you can actually isolate. So when we now look at this, is that a balanced equation? No. So now we would go through our rules. We have hydrogen or bromine. Okay? If we just blindly say, well, hydrogen was bad, which is okay, we can jump to the bromine. That's an eraser. How many bromines do I have?
2.
2 on the left and on the right? 1. Okay? First mistake you want to avoid. Don't do that. Okay? What you're now doing is changing your chemical formula. When you've started balancing an equation, you are making the assumption that your formulas were correct. Don't start changing the formulas. When you balance an equation, the only thing you can change would be the coefficient in front. How do I ensure that I get 2 bromines on the right-hand side?
And you put a 2 in front of HBr.
I put a 2 in front of the HBr. That 2 will apply to everything afterwards up to a mathematical operator, which there isn't one here. So that 2 applies to the H and it applies to the Br. Okay? So now I have 2. When it comes to work, I write the numbers that were there, and you'll usually see me do an arrow through it with the new number for how many to balance it. Okay? I can now move to my hydrogen. How many hydrogens on the left?
2.
How many hydrogens on the right?
2 now.
And it is now 2 now. The hydrogen's actually self-balanced. Okay? So now what is our step?
No, we go back and check.
Okay? This is where it's nice with a digital screen. You just erase it all and you start again. Okay? With yours, what I would recommend doing is you just write it down underneath it. Bromines on the left.
2.
Bromines on the right.
2.
Hydrogens on the right.
2.
Hydrogens underneath.
0.
Hydrogens on the left.
2.
This is where I get confused though.
Go for it.
Because, so bromine has, are we talking about the charges or not?
There's no addressal of charges.
That's where it is.
The only time charges come into play is looking at your formulas.
So then how do
You were
have
given,
bromines on the left?
how do you know you have 2 bromines on the left? What does that number 2 mean? What does that orange 2 mean?
Isn't the charge relevant to this?
What does that 2 mean? Answer my question
There's 2 of
first.
them.
That 2 applies to what is directly in front of it. What is directly in front of it? The bromine. There are 2 bromines. Does the charge have an effect on your equation? Yes. The charge changes the formula. At this point, we're balancing the equation. When we start balancing the equation, what does that mean about our formulas? The formulas must be correct. That is a different question. Okay? Unfortunately, it's a question that you have to answer before you can balance. Okay? How would you know you got them balanced?
Same amount of elements. Atoms will be the same.
Nope, that's balancing the equation. We're talking about balancing the formula and the charges within that formula.
You go through and write down the charges on there.
Chapter 6, nomenclature. Okay? That's how you would know you've got them properly balanced. Okay? That's the process that you should be getting in nomenclature with Chapter 6, is balancing those charges. If all you're getting out of Chapter 6 is that you can name a compound, you've done yourself a disservice, which is why I don't like the cheat method crossover from the textbook, because it gets you to a name, but it doesn't address the balancing of charge, which is of critical importance when you start balancing a chemical equation.
So, like, on the test though, we can rightfully assume that if you're giving us a chemical equation that you want us to balance, that the charges are already.
Yes, if I give you a whole chemical equation, you should be assuming that I gave it to you correctly, because that would be a real a-hole maneuver. Okay? But what I could do on the test is give you that equation and say, what is the sum of the coefficients of the balanced equation? And you'll be like, well, how do I balance it? I don't have products. Yep, because guess what you have to do? You have to predict the products. Okay? Which again, we haven't covered yet. Okay? So there's a lot of interconnection between each of these pieces. And so by doing balancing first, the chemical equation, we're trying to get you started with that process so you understand it. We then layer the difficulties in behind it. Those difficulties, so instead of doing a new example, are going to come in here, looking at a chemical equation and being able to classify it very quickly. So that when I go back and I saw, let's do this, that equation, I see metal, complex ion, metal, complex ion. I see cation, anion, cation, anion. That's a double replacement. How does that work? The metals exchange places. I get barium with sulfate. I get aluminum with nitrate. Okay. What is the charge on barium? Good. Looking to the periodic table. It's in the second column. It's a +2. What is the charge on sulfate? Looking at the periodic table is going to be problematic because it's not on the periodic table. Sulfate is a complex ion that you are required to have memorized, which means -2. Is that formula correct? Yes. What is the charge on aluminum? +3. Awesome. What is the charge on nitrate? Again, one of those complex ions you are required to have memorized. -3 would be a nice, easy answer. It's not. It's -1. Is that formula correct? No, those charges don't balance out. A +3 and a -1 don't balance. Those charges have to cancel. How does that cancel? Okay, I heard put a 2 in front of the nitrate. In a formula, do we have 2's in front? No. So when, okay, when you're talking about a 2, what are you trying to say? You want 2 nitrates. Where do we specify the amount for nitrates? We put it as a subscript afterwards. 32? Parentheses, 2. What's the charge now from our nitrate? -2. Did that balance? No, so 2 was wrong. 3. Now your formula is correct. Now that formula is correct. Now what can you do?
The left side of the equation.
Because that has nothing to do with the left side of the equation. Okay? We have not balanced the equation. We balanced the formula. Once the formula is correct, now what can we do? Now you can balance the equation. Okay? That's why it's a secondary step.
Is sulfide right?
What's that?
The, after parentheses, sulfide.
There's no sulfide in this. There's sulfate. Sulfate is a -2.
Sorry. There's a substitute outside of the parentheses.
For this sulfate?
Yeah.
Yes, that is correct. Okay? So you're like, but the other side is wrong. Okay, let's take a look at that. What's the charge on aluminum on the other side? It's still a +3. What's the charge on sulfate? -2. How do I make a +3 equal to a -2?
6.
Common multiple is 6. How do I make a +3 a 6?
Times 2.
Times it by 2. How do I make a -2 equal to 6?
Times it by 3.
Times it by 3. Okay? So, and that is exactly what will show up. And that one is actually an easy one, believe it or not. Okay? Where it becomes challenging is with structures like titanium oxide, because what people will go through and do is start misappropriating numbers and putting the wrong things in those because of the crossover method. Don't do the crossover method. Okay? It is wrong. Okay, if you don't know what the crossover method is, it's cool. Don't worry about it. If you're reading the textbook and it says crossover, just close your eyes, start flipping pages until it disappears. Okay? We have to be done there.